this is going to be a recap of what we did in the last lecture, and it's to be a basically a showroom of how to do this using the DL2 library. So basically, we will go a little bit further with respect to step number 2, and we will make step number 2 plot also the degrees of freedom, and we will try to understand how things actually work for finite element degrees of freedom, which are of arbitrary dimensions on general meshes. So just to give you a hint of what I would like to get to at the end of this lecture, I would like to get to this point, so to be able to plot these types of finite element spaces and to understand exactly how these are working and what is that we are currently doing. So the idea here is that each one of these elements that you see here, it's part of the triangulation in the background. And on top of this triangulation, one defines degrees of freedom, so distributes degrees of freedom. The distribution of degrees of freedom is done globally through the functions calls in the DL2 library called distribute degrees of freedom, so DOF handler distribute DOFs. And the degrees of freedom are in fact somehow the functionals that allow you to extract one single real value given a function that has given a function in the space which is infinite dimensional in the background. And the idea here is that at every basis function that you construct coincides one specific functional that makes sure that the coefficient that represents that basis function is multiplied with the correct number. And in reality, for Lagrangian basis functions, which is what we started doing in the previous 2 lectures ago, so last week, we had seen that the basis is constructed once you have the support points. So once you have defined what are the support points, and you have defined what is the meaning that you want to associate to the real number that you have, in particular, the basis functions are constructed in a canonical way. So that means every basis function is going to be one, whenever you evaluate the dual basis function on the primal basis function, this is going to be either 1 or 0, according whether the indices of the 2 functions are the same. And in other words, if you look at this from the linear point of view, so in this particular case, this is a space which is constructed on a grid, which is a quadrilateral grid. In each one of these cells is a quadrilateral. And on each one of these cells, we define 4 basis functions that actually fill up the full space, which is called Q1 space. And it's the tensor product of P1 in one direction and Q1 in the other direction. So there's 4 basis functions for these guys, namely, you can see the finite dimensional space of each one of these elements as the span of the constant one, x, y, and xy, which is the product of the 2. And of course, if you choose this basis function, you won't have the property that the basis function is equal to 1 on one vertex and 0 on the other vertices. And instead, you construct the basis functions that in such a way that this is satisfied. And now the idea here is that the basis functions, when you look at each one of these single cells, the basis function itself is a piecewise, well, it's a polynomial space. The plotting here is triangulated, so this looks like it's a triangle, but in reality, this is actually a function which is smooth like this, in this way. And you will see this better for the second order polynomials, because the part of you doesn't know how to show functions which are not linear on faces. And in fact, you see this because this function here is smooth from here to here and is smooth also from here to here, but the plotting doesn't show this. Okay. Now the idea is today I want to make sure that we understand exactly how these are constructed and exactly how these are distributed on the degrees of freedom. This is an essential, and it's also something that confuses students a lot in the first moment. So I would need to make sure that we are on the same page specifically for these types of reasons. In particular, we are going to restrict ourselves to the space capital D, which is the space H1. So we are going to consider the case where V is h1 of omega, and omega is included in Rd with d equal to 1, 2, or 3. And in particular, in this case, when you have the function v, which is in h1 of omega, what you want to obtain is a subspace which is a subspace of h1 of omega according to two ingredients. One, tau h, which is a triangulation actually three ingredients. Triangulation of omega. Let me make this set in green, meaning this is something that will be implemented. So green is whenever you see something which is in green, there is a one-to-one relationship with what is implemented in the code, and you will see this exactly in the code. According to the triangulation of omega, according to a reference finite element, and this is also an object that will need to be implemented, and a mapping between. And now we have seen this. I will go back to this in this recap today. So the reference finite element, we define this as a triple, the triple which is T hat, a polynomial space on T hat, and a basis for the dual of P hat T. So this is a sigma, the basis for the dual. Okay. And the mapping, also something that needs to be implemented in the code, the mapping between T hat and TK for every EK in the triangulation tau h. Now, of course, also this needs to be implemented in the library. So you need to have access to elements TK of the library. You have to have access to mapping that transform this element, the reference elements to these elements, to these standard cells in the triangulation. And of course, you need to satisfy continuity conditions for VH that has to be included in capital VH. And this is handled by a degrees of freedom handler that we have called DOF handler. And now today I would like to discuss in detail, how the DOF handler works and what it does in reality. Okay, so red boxes coincides with classes in DO2. Okay, so let's make a very short recap of what a reference finite element is. Okay, so the reference finite element doesn't specify how to construct a global finite element. So we have to understand how we construct it and why we construct it in this way. So start with the reference element. What we said is the following: start with T hat. And in 1D, we constructed this as a segment or a triangle, or a simplex in general, so the simplex. Okay, so what we are going to say today is about the simplices. The discussion for the case for quadrilateral cells or hexahedral cells is much simpler, and I'll show this at the very end of this part. Okay, so on T hat, what we would like to have choose is we choose a P of T hat finite dimensional. And what we have done so far for the Lagrangian case P of T hat was defined as polynomials of order K on T hat. So polynomials of order K. And now the discussion was, once you have defined the element and the space of polynomials of the element, we want to construct a basis for P of T hat prime and we do this through a selection of n T support points so this number, so let me not call it NT because otherwise we get let me do these directly as NFE support points. Okay, so this NFE is exactly equal to the dimension of P T hat. And as we said, P of T hat for general, so we had the following properties. For general dimensions D, the dimension of P of T hat is equal to, so let me write this in this way. So we have, so this is exactly equal to the dimension of polynomial of order K on T hat. And the idea here is to be explicit now about these numbers. And let's say I would like to understand what are these dimensions for D equals 0, 1, 2, and 3. And we already said that this is the case. So we had N1, N0, N2, and N3, and we'll stop here. And N0, it's equal to 0 if K is equal to 0, and 1 if K is greater or equal than 0, than 1. Okay, by convention. And the reason why I'm saying this is because if you're in dimension 0, that means you're just looking at a single point. You only have one degree of freedom if there is a degree of freedom associated with the given vertex. And this only happens by convention if you have degrees of freedom associated to vertices. So we say here that the number of degrees of freedom that we can associate to a vertex is equal to 1 if the dimension of, if K is equal to 1 or higher and is equal to 0 otherwise. And this is just a convention to generalize the discussion about the choose the support points in the general case. Okay, N1 instead is equal to k plus 1. So the 0 here refers to the dimension. Okay, so these numbers over here, and d, where d is dimension. Okay, so the idea here is these are points, and 1 is equal to k plus 1, and these are lines, and n2 is equal to 1/2 k plus 1, k plus 2, and these are triangles. And n3 is equal to 1/6 k plus 1, k plus 2, k plus 3 for tetrahedra. Okay. Now the idea that we would like to exploit here is that the selection of the support points in reality is arbitrary as long as you choose a number of support points which is equal to the dimension of the space, if you look at this only locally. The problem is that, you know, if you want to impose some sort of continuity between neighboring elements, for example, you cannot choose those points in an arbitrary manner. So the idea of Lagrangian finite element methods is that for the Lagrangian finite element methods, you associate the support points of these objects to lower dimensional objects for as much as you can, in such a way that the following property is satisfied. Okay, so if we want to have continuity in VH, then the issue is VH, so any function for every function VH in the space capital VH, then if K1 T, sorry, I used T in this slide, so T1 closure intersected T2 closure is different from the empty set. So if we have the two elements share something, say a vertex, or they share an edge, or they share a face, then what needs to happen is that VH restricted to the closure of T1 intersected T2 has to be equal on both sides. So it has to be single valued. Okay, so let me be precise about what I'm stating here. Consider the two-dimensional example, and the simple example that shows why this is how to choose support points in a good manner is that usually done is the following. So consider a simple triangulation that is made of two triangles. Okay, so triangle number 1 and triangle number 2. Okay, so these are this is T1, this is T2, and here we have the two vertices that are shared between these two guys, and the edge which is in between these two guys. Okay, now let me copy this on the side, and let's try to understand how you can choose a say for example that we have T1, and we want to construct polynomials of order 1 on T1 and sigma on T1. Okay, and let's assume for example, that we want the same thing on T2, P2 of T2, and sigma of T2, okay? And I'll show you two possible choices of support points. Which we will call AI. So for P1 in T1, we have support points AI that goes from from 1 to 3. So we have 3 degrees of freedom associated to triangles on every single element. So there's support points AI, and let's put AI, let me put a 1 somewhere. So we have, in reality, something like A1I here. So it's an object here, and we also have A2I for I that goes from 1 to 3. Okay. And now let's assume that we want to construct the basis functions using 3 arbitrary points on the triangles. Okay. Now let's take 3 arbitrary points on the triangle. So for example, let's say that I use as, so there's 3 cases that I would like to consider. So this one, side, and this one. Okay. So case 1, we choose as support points 3 arbitrary points on T1 and on T2. Okay. Case 1, we have that A1I is different from A2J for every IJ in 1, 2, and 3. So we have in total a total of 6 support points. Okay. 3 per triangles. Okay. 3, 4 each triangle. Okay. Now, if I take V1, if I take any function VH that can be written as VH restricted to T1, then there exists a unique set of VI. Let's call this function U instead of V, because I don't want to confuse this with the basis functions. Okay, so there exists a unique UI for I that goes from 1 to 3, such that UH on T1 is equal to UI. And now let me write this as V1I. Okay. And of course, you can write this VUI, V1I as the basis functions VI applied to UH multiplied by V1I. So I'm saying that the degrees of freedom, the local degrees of freedom, are constructed to VI. And I never said what those VIs are. So let's say that these are, let me write those as V1I. So we have VI of VKI are defined as Dirac delta distribution between X and a ki. Okay. So if I have this, what happens here is, let me write this more correctly as a linear application of the duality. So this is the same notation, but I'm doing this to make sure that this is an integral, so that is actually the evaluation of UH evaluated on Aij, which is exactly UH on AKI of V1I. Okay? So now let's try to understand what is happening here. What is happening here is that if I look at UH restricted on T1, and then I look at the same function restricted on T2, if I start with an UH which is continuous, then I do get a continuous function, because there is only one function which is linear on T1 and linear on T2 and continuous across the interface, because there is only one linear function that is continuous, that is linear also on the line. So the linearity transfers to the lower dimensional object. And the problem here is that there is not a one-to-one relationship with the number of degrees of freedom that I have and the dimension of the total space that I have. In other words, if I select 6 real numbers, so there exists a UI, let me call this U, as I used before, UKI in R2 by 3, which is R6, okay, such that UKI times VKJ, summation is implied, so UH equal to that, does not belong to C0 of T1 united T2 closure. Okay? And the reason is simple. The reason is you can select arbitrarily 2 functions here, and you can have objects which are absolutely non-continuous on the 2 planes. Okay? And why is this a problem? Well, this is a problem. I mean, it's not a problem if you're trying to construct the space VH. So this is okay if you want VH to be included in L2 of omega, but it's not okay if you want VH which is included in H1 of omega. So how do we solve this? How do we fix this? So now let's go to case 2, which is a little better. So let's do case 2. Let's assume that instead of having 6 points, we only have 5 points. So we select the midpoint of every edge. Okay. So in the case 2, now this is a little bit more difficult from the notational point of view, and this is what makes this confusing for many students. So case 2 is still not continuous. Okay, and the reason why it's still not continuous is simply because you only have 1 point in common between the two segments. And what you're asking here is that the function UH is equal to the value of the base of the degree of freedom here is going to be taken by the value of the function UH on the point which is in between the two. And if you take linear functionals on the 2 subspaces, so if you take linear functionals here, linear functions here, and linear functions here, there exists an infinite number of linear functions that share a single point, because you can have all situations in which two planes touch on one point. Okay? So this is still not enough to ensure continuity between T1 and T2. So case 2, and so let me write here, the dimension of case 1 is 6. The dimension of case 2 is 5. And 6 is 3 times n triangles. And here is 1 times n faces and edges. So the idea in the first case was we choose 3 arbitrary points. See that 3 arbitrary points is not enough to ensure continuity. Then we choose 3 points which are on the 3 faces. We say, okay, I know that the dimension of linear space in triangles is 3. So I have 3 faces. I can select 1 point per face, and I can put on every single face in the middle point 1 support point. And I make sure that I only choose 1 support point for each face. So if 2 triangles share a common support point, then I consider that to be a single degree of freedom, not 2 degrees of freedom on the 2 sides. Okay? If I do that, then what happens is that the total number of degrees of freedom that I have, if I consider the 2 triangles together, is 5. So I have 1, 2, 3, 4, and 5. And when I restrict to each one of these 2 guys, the set of degrees of freedom is 1, 2, 3 for T1, and 3, 4, 5 for T2. So let me repeat this again. For the numbering of the degrees of freedom that I constructed now, this is A1, A2, and A3. This is A4, this is A5, and this is A6. Now here I have A1, A2, and A3. And here I have A2, A4, and A5. Okay, so there's only 5 which are distinct and unique. Now, of course, if I look at every single triangle by itself, it has 3 support points. So I can define a basis for the dual space on T2. And these 3 support points are numbered according to the triangle. So here, one has to introduce the so-called local to global degrees of freedom indices. Local to global indexing. Okay, and it's done in the it's something which is which looks like the following. It's a matrix. Well, it's not, in general, it's not a matrix. It depends if the elements are the same, are all of the same size. But it's a vector of vectors, let's put it this way. Vector of vectors, in a certain sense. Okay, and it's such that LUG is the way you would find this in the fortune code Nastra. Okay, so local to global, and global to local is the way around. Okay? So local to global, KI gives you index of support point I on element K. And now the idea here is that we allow for elements to share some support points. And the reason why we want to allow this is because we want to ensure continuity between 2 neighboring elements if you want to have something which is enclosed, which is included in H1. So as we did for the triangles and for the triangulation, it's similarly to what happens with the triangulation. I don't know what's happening here. Sorry, my iPad froze for a second. I don't know what has happened. Okay, so now this seems to work again. Okay, sorry. So similarly to what happened for similarly to list of vertices and elements for triangulation. We need a list of support points. And notice that these two things are entirely separated from vertices. See, they are not necessarily vertices. They may be vertices, they may be vertices and something else, or they may be copies, multiple copies of vertices. So there's no relationship in general between vertices and support points, except the coincidence that sometimes they lay on the same physical space, physical position. A list of support points and a list of indices that refers to them for the definitions of FEM of the finite element on T, which is the triple T, pk of T. Now I'm restricting just to polynomials over K, and sigma of T. In particular, here is what is where this list will will play a big role. Okay, so let's go back to our example. Local to global Ki is the index of support points on I element K. So for a local to global, I will use the mathematical notations instead of the computer notation now. I'm saying here that L to G Ki, okay, in our case has K that goes from 1 to 2, and I always goes from 1 to 2 to 3. And in particular, this may be different only if you have mixed triangulation. So the second index can be different from 3. It can go to 4 or to 5 according to what is the dimension of what is the number of vertices. Sorry, the number of support points in each one of the things. This is especially true, for example, if you want to mix finite elements of different dimensions. Okay. So for the particular case 2, local to global 1 is a list of numbers which was 1, 2, and 3, while local to global 2 is a list of number that was 2, 4, and 5. Now let me just copy here this, otherwise we lose track of what was going on here. Okay, so this should make sense now. So you have a indexing of the number of support points that I'm using to describe that. And then on the side, there is a list of support points that tells you where are actually the locations of A1, A2, and A3. Okay, so what I'm saying here is that now, if I take sigma of tk is defined as the set of Dirac delta distribution centered on the vertex A, local to global, so that's L2G, of Ki, for I that goes from 1 to 3. Okay? Does that make sense? So if I now look at this definition is agnostic. It doesn't know anything about the fact that the finite dimensional space is continuous or not. So it doesn't know about that. It only knows that if you want to have a number, if you want to have a finite dimensional space of order 3, then you need 3 support points. So for the Lagrangian type of finite dimensional spaces, then you need 3 support points of order, you need 3 support points on the triangle, okay? And of course, this is reflected on the fact that you actually need to have on each one of the triangles 3 basis functions, 3 dual basis functions. So 3 objects that return to you a number whenever you apply those to a function, okay? Now the continuity of this is a fact which is set aside, and it's left over to the selection of the actual support points that you are allowing the problem to have. So we had in case 2 and in case 1 2 different types of situations. So the first situations that we had in case 1 was that the number L2G AI in that particular case, for case 1, L2G1 was still equal to 1, 2, 3, but L2G2 was equal to 2 to actually 1, 2, 3, 4, 5, and 6. And as you see, the maximum index that appears in this is 6, and the maximum inverse that appears in this is 5. Okay? And now let's go to the final case, which is case number 3. Well, case number 3 is the one that actually works. And let's put here now, case number 3. And the case number 3 is the case in which you put the dots or the crosses, according to how you write this, on the vertices of the triangulation. So this is A1, this is A2, this is A3, and this is A4. And now the dimension of this is 4. Now, the reason why the dimension of this is only 4, even if you have 2 linear spaces on the separate triangles, is because you do not allow the functions on triangle number 2 to be arbitrary. But you want the function on triangles number 2 to be the same function of triangle number 1, to be equal to the function on triangle number 1 for any arbitrary function of triangle number 1. And that is only possible if you allow the basis functions to be defined on the 2 vertices of the 2 triangles of the shared same edge, on the support points of defining the 2 vertices of the shared same edge. And let's understand exactly why this is the case. So what happens here is that, well, I mean, the reason why we want to understand this very clearly and very closely is because we want to be able to generalize this for higher order methods. Okay, so the idea here is that if you look at triangle number 2 and you impose the triangle number 2, that a function on triangle number 2 is given on the 2 vertices, where you already decided what the function was because of triangle number 1, then you're only left with 1 degree of freedom. You don't have 3 degrees of freedom to choose, but only 1. And it's how do you allow the functions to rotate in this direction by selecting a different number, a different value for the vertex number 4. But you cannot do anything else on vertices number 3 and 2 because those had already been chosen by triangle number 1. So if you start with triangle 1, you set 3 values of these functions. These uniquely identify 1 linear functions on T1, and in particular, a linear function also on the edge that joins A2 with A3. This edge in particular is shared with triangle number 2. So on triangle number 2, you want the value on A2 to A3 to be the same if you're looking for continuity. And if you're looking for continuity, then in case number 3, the only function that is left that you can choose, the only value that you can change on the second triangle is the value on the vertex A4. Does that make sense? So in case number 3, the local to global and now let me write this in blue because otherwise the local to global 1 is 1, 2, 3. And in the case number 2 is 2, 3, 4. Okay. Now here, I haven't been very careful about the orientation. Keep in mind that it would be mandatory and necessary for the implementation case to preserve the orientation. So particularly, I think I did the wrong selection of orientation in this particular case. So let me correct this right away. So be careful, because if I'm using A1, A2, A3, then the orientation on the other two should be either A3, A2, A4, or A4, A3, A2. All of these are equivalent, but not what I have selected. So you either say 2, 4, 3, or you say 3, 2, 4. Okay. And now, of course, the dimension of the space is smaller than the dimension of case 2, and is smaller than the dimension of case 1. And in this particular case, this space, so is continuous. And you can write this as UH is equal to UI VI. And now these indices, let me write this explicitly for a second. These go from 1 to 6. Okay? And there is a distinction between the local functions vi and the global functions vi. So you could write this as the sum of functions that are defined only locally. But the question here would be that if you want to have the uniqueness of the solution, so let me write, sorry, let me be explicit on how you write this. It's simpler to understand if you write this as two summations, sum for k that goes from 1 to 2, sum for I that goes from 1 to 2 of u h in a I k. And now aik is, I'll tell you exactly what this is in a second. So this is vki. Sorry, I used always vki. Okay. And now the question that I'm asking is this function continuous? Only in case 3. Okay. And the essential part here is that when I'm doing this summation, what is actually happening in the background is that for k equal 1, so this is T1, and then I have T2. Okay. So basically, I'm summing UH of A1, 1, V1, 1, plus all of them. And then I do UH of A21, V21, plus all of them. Okay. And the trick to understand what is happening is that we identify Vi with one single index with the degree of freedom associated to AI with one single index again. So this is the essential part of the discussion. And now I'll try to elaborate a little bit on this because I understand that this is usually not clearly understood by non-practitioners of finite element methods. So since it's arbitrary how to choose I mean, once you've selected the basis functions and selected the basis functions locally on T1 and T2, there is no reasons for these basis functions to be related to each other. And so the way to choose whether they relate to each other is to associate a global basis functions to each one of the local basis functions according to the support points globally to which these basis functions are associated to. So in particular, if Vkj has same support point of Vmi for k different from m, I can be equal to j, it doesn't matter, for k different from m and some pair ij, then we identify Vkj and Vmi with the same global basis function, which is V, and now here we have the global to local Ki, Kj. And if you write Kj is also the same as global to local Mi. Some pair ij. Does that make sense? So the idea is this. We identify this function, and it simply means that if I take V of global to local of Kj restricted to Tk is equal to the local Vk. Now I need to use a different notations with respect to the different that I'm using there. So let me use V tilde k here. So actually, let me stick to the notation that I had before with the two indices. So this is Vkj. Okay. So these are local basis functions local basis on Tk, we have that we write VH restricted to Tk is the span of Vkj for j that goes from 1 to n Tk, so depending on this, the size of this object. And we also have that Vkj for j that goes from 1 to nk, this is exactly sigma of Tk. So these are the dual basis functions. And we also have that the property that whenever you choose Vkj and you evaluate them on Vki, what you get is delta ij. Okay, so what I'm saying here is that I now indexing basically every finite element pair, triple, sorry. So the finite element triple is a local property of the, oops. Okay, so the finite element pair is, the finite element triple is given by the element, Tk, the basis functions, the local basis functions, which are canonical to the dual basis functions. So you construct Tk, the dual basis functions. And of course, implicitly here, I'm also writing Pk VH on Tk, this is equal to, I didn't write it explicitly, but it's exactly what this is equal to. So this is, now I've written the red thing. So let me move the red thing away for a second. And let me write this a little bit more compactly. So from what we did before, the triple is given by Tk I'm using too many Tk. This is called P. The notations that I had before, this is P of Tk. Okay. And now I should be able to do this. Okay. So if you look at this, guys, that we have over here, we have Tk, we have P of Tk, and we have sigma of Tk for every element Tk. And now what I'm saying here is that I identify the basis functions globally if the support point is locally identical. Okay? And this is only if you want continuity, of course. Okay? So if Vkj has the same support point of VMI, this is the property that you want to have for k different from m. So if you are on two different elements and you have some pairs of local indices I and j, then we identify Vkj and VMI with the same global basis functions, which is V of 2 global to local kj, which is equal to V of global to local mi. So let's look at an example here. Let's say, for example, we have two triangles. And now you understand the picture that we had that I showed at the beginning of the lecture. Okay, so we have two triangles. I don't like this non-symmetric triangle. And now we have here 1 point. And now let me plot this as if it was let me write on the background a do I have something straight that I can use? Yes, I do. So let's assume the triangulation is given by the thing on the background, and now I'm plotting this guy over here. So we have T1 here, T2 here, and here I have 4 superpoints, A1, A2, A3, and A4. And what I am plotting here on this graph is V4. Okay, so V4, which is coincident. Let me write this V4 in green. So V4 is defined as. Sorry, I have to interrupt for a second. Sorry, a package has just arrived. So V4 is equal to V1, 3. So locally, if I look at V1, 3, I am saying is it's the third basis function of triangle 1, and it's equal to V. So if so the idea would be the following. V4 restricted to T1 is equal to, using the same color code, V1, 3, while V4 restricted to T2 is equal to V2, 1. Okay, is it clear? This takes a little bit to digest. And now we are in the position to try to construct this for arbitrary Lagrangian finite element spaces. Okay, so how do we do this for arbitrary spaces? Well, the idea for arbitrary order we need to ensure that the support points, that the number of support points on the subelements of TK, and that's, for example, edges. So let's start with faces, edges, vertices. Okay, coincides with the dimension. Let me give a name to these subelements. So on the subelement X, let me call this capital X of Tk coincides with the dimension of what? Of the polynomial of order K restricted to X. Does that make sense? So we did write this in 2D. So let me give this again. Let me give this a name again. So let's go over here with, now we have this as N and D is equal to the dimensions of Tk on X, where X is manifold of intrinsic dimensions D. Okay. And as we said, we have N0 is equal to 0 or 1. Zero or 1 if K is equal to 0 or K greater equal than 1. And as we said, N1 in general, ND is equal to K over D in general, right? So I think this was the thing that I wrote, the binomial D plus K over K in general. Okay. So P1 continuous need one superpoint per vertex. Okay. P2 continuous need one superpoint per vertex but that's not enough, and one support point per edge per line, let's put it this way. Okay, so that's per vertex and per line. Okay. If you look at it in this way, with one support point per line, you exhaust all support points for the dimension of P2. So in 2 dimensions, for example, for P2, you get the situations in which you have that. You have 1, 2, 3. Those are one support point per vertex. This is a space which is P1. If I look at the edge, if I want to have a P2 space for the edge, I need 3 support points. And so I take an additional one and I put it in the edges. Okay? And since I have to have the restriction on each one of the sub-elements of the subspace contains the number of superpoints that are required to construct the space of the relevant dimension, then I exhausted the dimension of the superpoints in Q2, for example, for P2. Okay. In order to have points in the triangles for 2 dimensions, for example, inside the triangles, you need to go up to P3. We have P3, then P3, you have one superpoint vertex that exhausts 3 degrees of freedom. Now, if I restrict to an edge, I need to have 2 superpoints more, because on a line, a polynomial of order 3 is specified by 4 superpoints, 2 on the vertices and 2 inside the lines. And now I have 2 more here. I have 2 more here. And if you look at the dimensions in order 2, there's 1 missing, and the 1 missing is the one that is in the center here. Now, I'm not very good at drawing these things, but let's try to be more. Okay. And now, this is for P3. And now if you go to the 3 dimensions for P2 or for P3, you would have exactly the same situation. So you have to guarantee that the number of degrees of freedom that you specify on each one of the triangles that make up the 3-dimensional tetrahedra will have the same number of degrees of freedom that are required for P2 and P3 in 2 dimensions. Okay. Okay. And now, once you have done this, what happens is that you identify basically all of these degrees of freedom with the object that they are associated to, and the object, no matter whether the object is shared or not. So if a vertex has degrees of freedom associated to it, and several triangles share the same vertex, all of the triangles share that degree of freedom, and you only have 1 degree of freedom per vertex in the case of P1 global, for example. So let's take another example. So this gives you the concept of degree of freedom, or degrees of freedom per object in terms, in DL2 term. This is dPO vector. Okay, so dPO belongs to n d plus 1. Okay, and we have, typically, its indexed is dPO I is equal to n I, so the dimension of the basis functions that you want to have for Lagrangian finite element spaces. Okay, so this is called dPO in the library DL2, and it's what we have called so far NI, which stands for number of degrees of freedoms per object I. Or actually, sorry, this is not exactly NI, so let me take that back. Let me be careful. Degrees of freedom per object I is not dPi. It's a different thing. So it's number of superpoints on objects of intrinsic dimension I, excluding and this is the important part, excluding objects, sub-objects, excluding sub-objects. So let's go, for example, and go to an example of dPr for P1. Okay. So for P1 of TK, now degrees of freedom per object for P1 is dp of 0 is equal to 1, and dp of I is equal to 0 for I greater than 0. And this is in any dimension. So what it's telling you is that if you have P1, you only need to define degrees of freedoms on the vertices. And you don't need to specify any more degrees of freedom anywhere else. So on the vertices of triangulation, you associate 1 degree of freedom, and you don't associate any other degree of freedom on faces, on edges, and on triangles. And this doesn't mean that if you look at the face or at an edge, there are no degrees of freedom associated to that. It means that the associated degrees of freedom to an edge are associated to the vertices of the edge and not the edge itself. Does that make sense? So it's not the same thing, different. It's not the same thing. dPi is not equal to Ni, because it is equal. You could say the opposite. You could say that Ni is equal to the sum for j that goes from 0 to I of dPoj. This is what you can say. Okay, the number of degrees of freedom associated to so the dimension of the space that you're looking at restricted to an element of dimension I is equal to the sum of all the dimensions of all the degrees of freedom associated to the objects of smaller dimension with respect to that guy. Does that make sense? And of course, if you look at the number of degrees of freedom, so ntk, which is the dimension of the space defined on tk, simply the sum from the j goes from 0 to d of dPoj. Does that make sense? Is it clear? Okay, so now that we have this, I would like to spend the last few minutes, and then I will give you the possibility to participate to the CISA welcoming CISA video registration at 12:30. We take a 10 minutes break. We can restart afterwards, or we simply go back to the next week if this is a lot to digest. So let me just share for the moment the following piece of code that I wrote in the other that I wrote for our. So you should be able to see my screen, I hope. No. Yes. Can you see my screen?
Yes.
Okay. So I've made basically a modification of step 2. And the modification of step 2 is intended to plot degrees of freedom associated to a hypershell in which I distribute a finite element of degree and FEQ of degree. In the case of FEQ, the dimensions is much simpler in the sense that the dimension of an FEQ of dimension dim is equal to the dimension of P1 in one dimension elevated to, or the dimension of PK on one dimension is elevated to the dimension dim. So you just have a multiplication, you elevate to power dim, whatever dimensions you have in one dimension, okay? So the FE degree that you have here is the finite element space of degree, and I'm taking this from the command line. So I'm taking, constructing the command line, refining 0 times or 1 times, and I'm taking the degree from the command line as the first argument on the command line after the executable is the refinement numbers, and the second argument is instead the degree of the polynomial space. I'll give this to you, okay? And now what I do is I do the following thing. I construct the triangulation, I distribute degrees of freedom globally, using the Dov-Handler distribute Dovs. This Dov-Handler distribute Dovs call does exactly what we have been discussing today. So it understands, it takes the finite element, it queries to the finite element what is the degrees of freedom per object that you have. So this is finite element DLI. You will ask this object to, you can ask this object to the finite element space. So if you finite element DLI, there should be a finite element class, okay, which is this one. Okay, so the finite element class contains a useful set of objects. There should be DPO degrees of. So this is usually done just for the Lagrangian finite element. So this is in the FEQ class, which you will see in a second. FEQ, probably better here. FEQ class, which is this guy over here, is all members. Get DPL vector is what will be returned exactly today and what we discussed today, only for internal use, of course, but its full name is guess Dovs per object vector function, and it creates Dov per objects vector functions. Okay, you cannot access this thing directly, but you will understand exactly how this is used in the Lagrangian case that we discussed today. Okay, so in the Lagrangian case that we discussed today, this is usually annotated. So any support point for finite element spaces are usually denoted with dots. And the dots, whenever you see a notation with the dots, means there is a Dirac delta distribution there. And that's exactly the notation that is used to express dual basis functions, which are evaluation of functions at points. So those are the points that define the basis functions by the canonical notation of the basis functions. And you can assume that whenever you have a collection of dots as basis functions, your basis functions are going to be different with respect to, your basis functions are going to be 1 in one of those dots and 0 elsewhere. So let me write here in this things, I forgot to do something, which was mapping FE degree, that out ATP flux, data out set flux. And now I would like to build and run this for a couple of guys. So the first one that you saw was this guy, and this guy here is exactly the linear basis functions. Okay, so this is the one that I was showing to you. Let me go back to the two-dimensional representations, which is probably easier to understand in terms of graphical perspective that you have here. So let's not warp by scalar. So you see here, I'm plotting basis function 1, and I am plotting the value of basis functions 1 as color-coded. So the color-coded values, red is 1 and blue is 0. So for the basis function 1, which is this one here, or I have also basis function 0 if you want, we can start from basis function 0, then that basis function is 1 on this point, is 0 in all other points. And if you look at this as a global function restricted to every element, is a Q1 function. So it's a scalar, it's a tensor product between P1 function in one dimensions and P1 functions in the other dimensions. Okay. Now, no matter which one you choose, all of these functions here are defined through support points. So if the support point is a global one, then it is shared among all the elements that have that support point in common. And in particular here, the degrees of freedom per objects of this finite element space is 1 per vertex and 0 elsewhere, which is exactly what I wrote before. So I'm associating 1 degree of freedom on each one of the vertices, and 0 degrees of freedom on every other guys. Okay. Now, what I would like to do is to run the same thing for the case with zero, actually with 1 refinement and polynomial 2. And now I should be able to copy this here. And if I now go to the second example, this is the second example. Now, if you look at this example, you should see that if you look at every one of the functions on top of this, the support points look like the one in the bracket. I don't know why this is not showing up now. Let me set the opacity a little bit lower. Okay. Okay. And now here, this is a quadratic basis function. I've done one local refinement. Probably one global refinement is not necessary to understand this for higher order polynomials. So let's do just one polynomial basis functions here. So the way that I did this, that I generated this graph, is the following. So if you look at this now, you see one element that you have here contains 1 degree of freedom per vertex, 1 degree of freedom per face, and 1 degree of freedom per cell. And this exhausts the degrees of freedom that you have on Q2 finite element spaces, which means it's a polynomial of order 2 in one direction times a polynomial of order 2 in the other direction. And now, of course, if you select any one of these spaces and you plot this, you will see that this spaces is equal to 1 here and 0 in all other points. More interestingly here, I can plot, for example, basis number 3 or 4. That's one basis here. This basis is shared among 2 objects, and it ensures continuity. So if I look at the restriction of these spaces on this edge, it's the same as the restriction from one side, is the same and from the other side. And the reason why this is possible is because the support points that define the basis functions on these cells are shared on the faces with the ones that are on the other side. So globally, the indices that I have here are associated with the number that you see here on the basis functions that I have there. The way that I generate this is by simply looping over, creating a vector of Rn in a certain sense, and this vector of Rn is here. It's the vector of basis functions. And this vector of basis functions is plotted then. And what I'm doing here is that for each one of these vectors, I simply set it to 0. So it's a vector of Rn with 0 entries, except one of those entries, which is equal to 1. So this represents graphically exactly the basis functions whose degree of freedom is equal to 1 in one basis and 0 elsewhere. So if you look at this plot, you will see here, this is the basis function, which is equal to 1 here and 0 elsewhere. And it's a polynomial of order 2 in each coordinate directions here. So if I warp this by scalar, you will see this as a nonlinear subdivision level, a higher nonlinear subdivision level. We show this a little bit better. Now, you should see this as a second order polynomials in each one of the coordinate directions. And so if you look at this, along this direction is a second order polynomial, which is 1 in one point, which is this point over here, and 0 in the 2 other points. And this second order polynomial identifies a basis, which is here, and it identifies the same basis with different numbering on the other side of the polynomials. So the same basis is this guy over here. And if you restrict to the local cell here, this is going to be basis number 1. And if you restrict to this cell, there's going to be basis number 7, for example. Okay, I'm just giving the correct numberings here. So let me stop here, and I would like you to play a little bit around with this, and I will commit these things onto the code. Let me just plot the third case, which is the third order polynomials. And let me just copy them over from the remote computer where I'm running these things. And let's try to go to the next case. So the next case, it's even more interesting. And the reason why it's even more interesting is because now these are third order polynomials, and they keep oscillating, and they will oscillate more and more along the various edges. And as you see, differently from what happens with the first order polynomial, this is all these basis functions contain both positive and negative values, but they are exactly interpolating polynomials on each one of these points. Okay, so let me just take a little break so that we can connect to the Zoom welcome by Sisa, and then I'll take any answers and any questions that you might have.